Section 4.3, Hooking Up Other Systems. Now that we've worked out how templating works, let's continue the use case by processing the hourly Wikipedia page views. The following two operators will extract the archive and process the extracted file by scanning over it and selecting the page view counts for the given page names. The result is then printed in the logs. This prints, for example, Apple, 31, Microsoft, 87, Amazon, 7, Facebook, 228, Google, 275. As a first improvement, we'd like to write these counts to our own database, which allow us to query it with SQL and ask questions such as, what is the average hourly page view count on the Google Wikipedia page? Figure 4.12. We have a Postgres database to store the hourly page views. The table to keep the data contains 3 columns, shown in listing 4.16. The page name and page view count columns, respectively, hold the name of the Wikipedia page and the number of page views for that page for a given hour. The date time column will hold the date and time for the count, which equals Airflow's execution_date for an interval. An example insert query would look as follows. This code currently prints the found page view count, and now we want to connect the dots by writing those results to the Postgres table. The Python operator currently prints the results, but does not write to the database, so we need a second task to write the results. In Airflow, there are 2 ways of passing data between tasks. By using the Airflow metastore to write and read results between tasks, this is called XCOM and covered in Chapter 5. By writing results to and from a persistent location, for example, disk or database, between tasks. Airflow tasks run independently of each other, possibly on different physical machines depending on your setup, and therefore cannot share objects in memory. Data between tasks must therefore be persisted elsewhere, where it resides after a task finishes and can be read by another task. Airflow provides one mechanism out of the box called XCOM, which allows storing and later reading any pickleable object in the Airflow metastore. Pickle is Python's serialization protocol, and serialization means converting an object in memory to a format that can be stored on disk to be read again later, possibly by another process. By default, all objects built from basic Python types, for example, string, int, dict, list, can be pickled. Examples of non-pickleable objects are database connections and file handlers. Using XCOMs for storing pickled objects is only suitable for smaller objects. Since Airflow's metastore, typically a MySQL or Postgres database, is finite in size and pickled objects are stored in blobs in the metastore, it's typically advised to apply XCOMs only for transferring small pieces of data, such as a handful of strings, for example, a list of names. The alternative for transferring data between tasks is to keep the data outside Airflow. The number of ways to store data are limitless, but typically a file on disk is created. In the use case, we've fetched a few strings and integers, which in itself are not space-consuming. With the idea in mind that more pages might be added, and thus data size might grow in the future, we'll think ahead and persist the results on disk instead of using XCOMs. In order to decide how to store the intermediate data, we must know where and how the data will be used again. Since the target database is a Postgres, we'll use the Postgres operator to insert data. First, we must install an additional package to import the Postgres operator class in our project. Airflow 2 Providers Packages. Since Airflow 2, most operators are installed via separate pip packages. This avoids installing dependencies you probably won't use while keeping the core Airflow package small. All additional pip packages are named. Only a few core operators remain in Airflow, such as the bash operator and Python operator. Refer to the Airflow documentation to find the Apache Airflow Providers package for your needs. The Postgres operator will run any query you provide it. Since the Postgres operator does not support inserts from CSV data, we will first write SQL queries as our intermediate data first. Running this task will produce a file, /tmp/postgres my_query.sql for the given interval, containing all the SQL queries to be run by the Postgres operator. See the following example. Now that we've generated the queries, it's time to connect the last piece of the puzzle. The corresponding graph view will look like figure 4.13. The Postgres operator requires filling in only 2 arguments to run a query against a Postgres database. Intricate operations such as setting up a connection to the database and closing it after completion are handled under the hood. The Postgres_CONN_ID argument points to an identifier holding the credentials to the Postgres database. Airflow can manage such credentials, stored encrypted in the metastore, and operators can fetch one of the credentials when required. Without going into detail, we can add the my_Postgres connection in Airflow with the help of the CLI. The connection is then visible in the UI. It can also be created from there. Go to Admin Connections to view all connections stored in Airflow, figure 4.14. Once a number of DAG runs have completed, the Postgres database will hold a few counts. There's a number of things to point out in this last step. The DAG has an additional argument, template_search path. Besides a string, insert into, the content of files can also be templated. Each operator can read and template files with specific extensions by providing the file path to the operator. In the case of the Postgres operator, the argument SQL can be templated, and thus a path to the file holding an SQL query can also be provided. Any file path ending in .sql will be read, templates in the file will be rendered, and the queries in the file will be executed by the Postgres operator. Again, refer to the documentation of the operators and check the field template_ext, which holds the file extensions that can be templated by the operator. Note: Jinja requires you to provide the path to search for files that can be templated. By default, only the path of the DAG file is searched for, but since we've stored it in /tmp, Jinja won't find it. To add paths for Jinja to search, set the argument template_search path on the DAG, and Jinja will traverse the default path plus additional provided paths to search for. Postgres is an external system, and Airflow supports connecting to a wide range of external systems with the help of many operators in its ecosystem. This does have an implication. Connecting to an external system often requires specific dependencies to be installed, which allow connecting and communicating with the external system. This also holds for Postgres. We must install the package Apache Airflow Providers Postgres to install additional Postgres dependencies in our Airflow installation. The many dependencies is one of the characteristics of any orchestration system. In order to communicate with many external systems, it is inevitable to install many dependencies. Upon execution of the Postgres operator, a number of things happen. Figure 4.15. The Postgres operator will instantiate a so-called hook to communicate with Postgres. The hook deals with creating a connection, sending queries to Postgres, and closing the connection afterward. The operator is merely passing through the request from the user to the hook in this situation. Note: an operator determines what has to be done. A hook determines how to do something. When building pipelines like these, you will only deal with operators and have no notion of any hooks, because hooks are used internally in operators. After a number of DAG runs, the Postgres database will contain a few records extracted from the Wikipedia page views. Once an hour, Airflow now automatically downloads the new hourly page views dataset, unzips it, extracts the desired counts, and writes these to the Postgres database. We can now ask questions, such as, at which hour is each page most popular? This listing gives us the most popular time to view given pages is between 1600 and 2100, shown in Table 4.2. With this query, we have now completed the envisioned Wikipedia workflow, which performs a full cycle of downloading the hourly page view data, processing the data, and writing results to a Postgres database for future analysis. Airflow is responsible for orchestrating the correct time and order of starting tasks. With the help of the task runtime context and templating, code is executed for a given interval, using the date-time values that come with that interval. If all is set up correctly, the workflow can now run until infinity. Summary. Some arguments of operators can be templated. Templating happens at runtime. Templating the Python operator works different from other operators. Variables are passed to the provided callable. The result of templated arguments can be checked with Airflow tasks render. Operators can communicate with other systems via hooks. Operators describe what to do. Hooks determine how to do work. Chapter 5. Defining dependencies between tasks. This chapter covers examining how to define task dependencies in an Airflow DAG, explaining how to implement joins using trigger rules, showing how to make tasks conditional on certain conditions, giving a basic idea of how trigger rules affect the execution of your tasks, demonstrating how to use XCOMs to share state between tasks, examining how Airflow 2's TaskFlow API can help simplify Python-heavy DAGs. In previous chapters, we saw how to build a basic DAG and define simple dependencies between tasks. In this chapter, we will further explore exactly how task dependencies are defined in Airflow and how these capabilities can be used to implement more complex patterns, including conditional tasks, branches, and joins. Toward the end of the chapter, we'll also dive into XCOMs, which allow passing data between different tasks in a DAG run, and discuss the merits and drawbacks of using this type of approach. We'll also show how Airflow 2's new TaskFlow API can help simplify DAGs that make heavy use of Python tasks and XCOMs. Section 5.1. Basic Dependencies. Before going into more complex task dependency patterns, such as branching and conditional tasks, let's first take a moment to examine the different patterns of task dependencies that we've encountered in the previous chapters. This includes both linear chains of tasks, tasks that are executed one after another, and fan-out, fan-in patterns, which involve one task linking to multiple downstream tasks or vice versa. To make sure we're all on the same page, we'll briefly go into the implications of these patterns in the next few sections. Section 5.1.1. Linear Dependencies. So far, we've mainly focused on examples of DAGs consisting of a single linear chain of tasks. For example, our rocket launch picture fetching DAG from Chapter 2, Figure 5.1, consisted of a chain of 3 tasks, one for downloading launch metadata, one for downloading the images, and one for notifying us when the entire process has been completed. In this type of DAG, each task must be completed before going to the next, because the result of the preceding task is required as input for the next. As we have seen, Airflow allows us to indicate this type of relationship between 2 tasks by creating a dependency between them using the write bit shift operator. Task dependencies effectively tell Airflow that it can only start executing a given task once its upstream dependencies have finished executing successfully. In the example, this means that get_pictures can only start executing once download_launches has run successfully. Similarly, notify can only start once the get_pictures task has been completed without error. One advantage of explicitly specifying task dependencies is that it clearly defines the implicit ordering in our tasks. This enables Airflow to schedule tasks only when their dependencies have been met, which is more robust than, for example, scheduling individual tasks one after another using cron and hoping that preceding tasks will have completed by the time the second task is started. Figure 5.2. Moreover, any errors will be propagated to downstream tasks by Airflow, effectively postponing their execution. This means that in the case of a failure in the download_launches task, Airflow won't try to execute the get_pictures task for that day until the issue with download_launches has been resolved. Section 5.1.2. Fan-in-out dependencies. In addition to linear chains of tasks, Airflow's task dependencies can be used to create more complex dependency structures between tasks. For an example, let's revisit our umbrella use case from Chapter 1, in which we wanted to train a machine learning model to predict the demand for our umbrellas in the upcoming weeks based on the weather forecast. As you might remember, the main purpose of the umbrella DAG was to fetch weather and sales data daily from two different sources and combine the data into a dataset for training our model. As such, the DAG, figure 5.2, starts with two sets of tasks for fetching and cleaning our input data. One for the weather data, fetch_weather and clean_weather, and one for the sales data, fetch_sales and clean_sales. These tasks are followed by a task, join_datasets, that takes the resulting cleaned sales and weather data and joins them into a combined dataset for training a model. Finally, this dataset is used to train the model, train_model, after which the model is deployed by the final task, deploy_model. Thinking about this DAG in terms of dependencies, there is a linear dependency between the fetch_weather and clean_weather tasks, as we need to fetch the data from our remote data source before we can do any cleaning of the data. However, because the fetching, cleaning of the weather data is independent of the sales data, there is no cross-dependency between the weather and sales tasks. This means we can define the dependencies for the fetch and clean tasks as follows. Upstream of the two fetch tasks, we also could have added a dummy start task representing the start of our DAG. In this case, this task is not strictly necessary, but it helps illustrate the implicit fan-out occurring at the beginning of our DAG, in which the start of the DAG kicks off both the fetch_weather and fetch_sales tasks. Such a fan-out dependency, linking one task to multiple downstream tasks, could be defined as follows. In contrast to the parallelism of the fetch-clean tasks, building the combined dataset requires input from both the weather and sales branches. As such, the join_datasets task has a dependency on both the clean_weather and the clean_sales tasks, and can run only once both these upstream tasks have been completed successfully. This type of structure, where one task has a dependency on multiple upstream tasks, is often referred to as a fan-in structure, as it consists of multiple upstream tasks fanning into a single downstream task. In Airflow, fan-in dependencies can be defined as follows. After fanning in with the join_datasets task, the remainder of the DAG is a linear chain of tasks for training and deploying the model. Combined, this should give something similar to the DAG shown in figure 5.3. What do you think happens if we now start executing this DAG? Which tasks will start running first? Which tasks do you think will not be running in parallel? As you might expect, if we run the DAG, Airflow will start by first running the start task, figure 5.4. After the start task completes, it will initiate the fetch_sales and fetch_weather tasks, which will run in parallel, assuming your Airflow is configured to have multiple workers. Completion of either of the fetch tasks will result in the start of the corresponding cleaning tasks, clean_sales or clean_weather. Only once both the clean tasks have been completed can Airflow finally start executing the join_datasets task. Finally, the rest of the DAG will execute linearly, with train_model running as soon as the join_datasets task has been completed and deploy_model running after completion of the train_model task. Section 5.2. Branching. Imagine that you just finished writing the ingestion of sales data in your DAG when your coworker comes in with some news. Apparently, management decided that they are going to switch ERP systems, which means that our sales data will be coming from a different source, and of course in a different format, in 1 or 2 weeks. Obviously, this change should not result in any disruption in the training of our model. Moreover, they would like us to keep our flow compatible with both the old and new systems, so that we can continue to use historical sales data in our future analyses. How would you go about solving this problem? Section 5.2.1. Branching within tasks. One approach could be to rewrite our sales ingestion tasks to check the current execution date and use that to decide between two separate code paths for ingesting and processing the sales data. For example, we could rewrite our sales cleaning task to something like this. In this example, _clean _sales _old is a function that does the cleaning for the old sales format, and _clean _sales _new does the same for the new format. As long as the result of these is compatible, in terms of columns, data types, etc., the rest of our DAG can stay unchanged and doesn't need to worry about differences between the two ERP systems. Similarly, we could make our initial ingestion step compatible with both ERP systems by adding code paths for ingesting from both systems. Combined, these changes would allow our DAG to handle data from both systems in a relatively transparent fashion, as our initial fetching, cleaning tasks make sure that the sales data arrives in the same processed format, independent of the corresponding data source. An advantage of this approach is that it allows us to incorporate some flexibility in our DAGs without having to modify the structure of the DAG itself. However, this approach works only in cases where the branches in our code consist of similar tasks. Here, for example, we effectively have two branches in our code that both perform a fetching and cleaning operation with minimal differences. But what if loading data from the new data source requires a very different chain of tasks? Figure 5.5. In that case, we may be better off splitting our data ingestion into two separate sets of tasks. Another drawback of this approach is that it is difficult to see which code branch is being used by Airflow during a specific DAG run. For example, in Figure 5.6, can you guess which ERP system was used for this specific DAG run? This seemingly simple question is quite difficult to answer using only this view, as the actual branching is hidden within our tasks. One way to solve this is to include better logging in our tasks. But as we will see, there are also other ways to make branching more explicit in the DAG itself. Finally, we can only encode this type of flexibility into our tasks by falling back to general Airflow operators, such as the Python operator. This prevents us from leveraging functionality provided by more specialized Airflow operators, which allow us to perform more complicated work with minimal coding effort. For example, if one of our data sources happened to be a SQL database, it would save us a lot of work if we could simply use the MySQL operator to execute a SQL query, as this allows us to delegate the actual execution of the query, together with authentication, etc., to the provided operator. Fortunately, checking for conditions within tasks is not the only way to perform branching in Airflow. In the next section, we will show how to weave branches into your DAG structure, which provides more flexibility than the task-based approach. Section 5.2.2, Branching within the DAG. Another way to support the two different ERP systems in a single DAG is to develop two distinct sets of tasks, one for each system, and allow the DAG to choose whether to execute the tasks for fetching data from either the old or new ERP system, Figure 5.7. Building the two sets of tasks is relatively straightforward. We can simply create tasks for each ERP system separately using the appropriate operators and link the respective tasks. Now we still need to connect these tasks to the rest of our DAG and make sure that Airflow knows which it should execute when. Fortunately, Airflow provides built-in support for choosing between sets of downstream tasks using the branch Python operator. This operator is, as the name suggests, similar to the Python operator in the sense that it takes a Python callable as one of its main arguments. However, in contrast to the Python operator, callables passed to the branch Python operator are expected to return the ID of a downstream task as a result of their computation. The returned ID determines which of the downstream tasks will be executed after completion of the branch task. Note that you can also return a list of task IDs, in which case Airflow will execute all referenced tasks. In this case, we can implement our choice between the two ERP systems by using the callable to return the appropriate task_ID, depending on the execution date of the DAG. This way, Airflow will execute our set of old ERP tasks for execution dates occurring before the switch date, while executing the new tasks after this date. Now, all that needs to be done is connect these tasks with the rest of our DAG. To connect our branching task to the start of the DAG, we can add a dependency between our previous start task and the pick_ERP_system task. Similarly, you might expect that connecting the two cleaning tasks is as simple as adding a dependency between the cleaning tasks and the join_datasets task, similar to our earlier situation where clean_sales was connected to join_datasets. However, if you do this, running the DAG would result in the join_datasets task and all its downstream tasks being skipped by Airflow. You can try it out if you wish. The reason for this is that, by default, Airflow requires all tasks upstream of a given task to complete successfully before the task itself can be executed. By connecting both of our cleaning tasks to the join_datasets task, we create a situation where this can never occur, as only one of the cleaning tasks is ever executed. As a result, the join_datasets task can never be executed and is skipped by Airflow, figure 5.8. This behavior that defines when tasks are executed is controlled by so-called trigger rules in Airflow. Trigger rules can be defined for individual tasks using the trigger_rule argument, which can be passed to any operator. By default, trigger rules are set to all_success, meaning that all parents of the corresponding task need to succeed before the task can be run. This never happens when using the branch Python operator, as it skips any tasks that are not chosen by the branch, which explains why the join_datasets task and all its downstream tasks were also skipped by Airflow. To fix this situation, we can change the trigger rule of join_datasets so that it can still trigger if one of its upstream tasks is skipped. One way to achieve this is to change the trigger rule to none_failed, which specifies that a task should run as soon as all of its parents are done with executing and none have failed. This way, join_datasets will start executing as soon as all of its parents have finished executing without any failures, allowing it to continue its execution after the branch. Figure 5.9. One drawback of this approach is that we now have 3 edges going into the join_datasets task. This doesn't really reflect the nature of our flow, in which we essentially want to fetch sales, weather data, choosing between the 2 ERP systems first, and then feed these 2 data sources into join_datasets. For this reason, many people choose to make the branch condition more explicit by adding a dummy task that joins the different branches before continuing with the DAG. Figure 5.10. To add such a dummy task to our DAG, we can use the built-in dummy operator provided by Airflow. This change also means that we no longer need to change the trigger rule for the join_datasets task, making our branch more self-contained than the original. Section 5.3. Conditional tasks. Airflow also provides you with other mechanisms for skipping specific tasks in your DAG depending on certain conditions. This allows you to make certain tasks run only if certain datasets are available, or only if your DAG is executing for the most recent execution date. For example, in our umbrella DAG, figure 5.3, we have a task that deploys every model we train. However, consider what happens if a colleague makes some changes to the cleaning code and wants to use backfilling to apply these changes to the entire dataset. In this case, backfilling the DAG would also result in deploying many old instances of our model, which we certainly aren't interested in. Section 5.3.1. Conditions within tasks. We can avoid this issue by changing the DAG to only deploy the model for the most recent DAG run, as this ensures we only deploy one version of our model, the one trained on the most recent dataset. One way to do this is to implement the deployment using the Python operator and explicitly checking the execution date of the DAG within the deployment function. Although this implementation should have the intended effect, It has the same drawbacks as the corresponding branching implementation. It confounds the deployment logic with the condition. We can no longer use any other built-in operators than the Python operator, and tracking of task results in the Airflow UI becomes less explicit. Figure 5.11. Section 5.3.2. Making tasks conditional. Another way to implement conditional deployments is to make the deployment task itself conditional, meaning that it is only executed based on a predefined condition, in this case whether the DAG run is the most recent. In Airflow, you can make tasks conditional by adding a task to the DAG that tests the said condition and ensures any downstream tasks are skipped if the condition fails. Additionally, we can make our deployment conditional by adding a task that checks if the current execution is the most recent DAG execution, and adding our deployment task downstream of this task. This now means that our DAG should look something like what's shown in Figure 5.12, with the train_model task now connected to our new task and the deploy_model task downstream of this new task. Next, we need to fill in our _latest_only function to make sure that downstream tasks are skipped if the execution_date does not belong to the most recent run. To do so, we need to check our execution date and, if required, raise an Airflow skip exception from our function, which is Airflow's way of allowing us to indicate that the condition and all its downstream tasks should be skipped, thus skipping the deployment. This gives us something like the following implementation for our condition. We can check if this does what we expect by executing our DAGs for a few dates. This should show something similar to Figure 5.13, where we see that our deployment task has been skipped in all DAG runs except the last one. How does this work? Essentially, what happens is that when our condition task, latest_only, raises an Airflow skip exception, the task is finished and assigned a skipped state. Next, Airflow looks at the trigger rules of any downstream tasks to determine if they should be triggered. In this case, we only have one downstream task, the deployment task, which uses the default trigger rule all_success, indicating that the task should only execute if all its upstream tasks are successful. In this case, this is not true as its parent, the conditional task, has a skipped state rather than success, and therefore the deployment is skipped. Conversely, if the condition task does not raise an Airflow skip exception, it completes successfully and is given a success status. As such, the deployment task gets triggered as all its parents have completed successfully, and we get our deployment. Section 5.3.3. Using built-in operators. As only running tasks for the most recent DAG run is a common use case, Airflow also provides the built-in latest-only operator class. This operator effectively performs the same job as our custom-built implementation based on the Python operator. Using the latest-only operator, we can also implement our conditional deployment like this, which saves us writing our own complex logic. Of course, for more complicated cases, the Python operator-based route provides more flexibility for implementing custom conditions. Section 5.4. More about trigger rules. In the previous sections, we have seen how Airflow allows us to build dynamic behavior DAGs, which allows us to encode branches or conditional statements directly into our DAGs. Much of this behavior is governed by Airflow's so-called trigger rules, which determine exactly when a task is executed. We skipped over trigger rules relatively quickly in the previous sections, so now we'll explore what they represent and what you can do with them in more detail. To understand trigger rules, we first have to examine how Airflow executes tasks within a DAG run. In essence, when Airflow is executing a DAG, it continuously checks each of your tasks to see whether it can be executed. As soon as a task is deemed ready for execution, it is picked up by the scheduler and scheduled to be executed. As a result, the task is executed as soon as Airflow has an execution slot available. So how does Airflow determine when a task can be executed? That is where trigger rules come in. Section 5.4.1. What is a trigger rule? Trigger rules are essentially the conditions that Airflow applies to tasks to determine whether they are ready to execute, as a function of their dependencies, equals preceding tasks in the DAG. Airflow's default trigger rule is all_success, which states that all of a task's dependencies must have completed successfully before the task itself can be executed. To see what this means, let's jump back to our initial implementation of the umbrella DAG, figure 5.4, which does not use any trigger rules other than the default all_success rule. If we were to start executing this DAG, Airflow would start looping over its tasks to determine which tasks can be executed. That is, which tasks have no dependencies that have not been completed successfully. In this case, only the start task satisfies this condition by not having any dependencies. As such, Airflow starts executing our DAG by first running the start task, figure 5.14a. Once the start task has been completed successfully, the fetch_weather and fetch_sales tasks become ready for execution, as their only dependency now satisfies their trigger rule, figure 5.14b. By following this pattern of execution, Airflow can continue executing the remaining tasks in the DAG until the entire DAG has been executed. Section 5.4.2. The effect of failures. Of course, this only sketches the situation for a happy flow in which all our tasks complete successfully. What, for example, happens if one of our tasks encounters an error during execution? We can easily test this by simulating a failure in one of the tasks. For example, by simulating a failed fetch_sales task, we can see that Airflow will record the failure by assigning the fetch_sales the failed state rather than the success state, figure 5.15. This means that the downstream clean_sales task can no longer be executed, as it requires fetch_sales to be successful. As a result, the clean_sales task is assigned the state upstream_failed, which indicates that it cannot proceed as a result of the upstream failure. This type of behavior, where the result of upstream tasks also affects downstream tasks, is often referred to as a propagation, as in this case the upstream failure is propagated to the downstream tasks. The effects of skipped tasks can also be propagated downstream by the default trigger rule, resulting in all tasks downstream of a skipped task also be skipped. This propagation is a direct result of the definition of the all_success trigger rule, which requires all of its dependencies to have been completed successfully. As such, if it encounters a skip or failure in a dependency, it has no other option than to fail in the same manner, thus propagating the skip or failure. Section 5.4.3. Other trigger rules. Airflow also supports several other trigger rules. These rules allow for different types of behavior when responding to successful, failed, or skipped tasks. For example, let's look back at our branching pattern between the two EPR systems in section 5.2. In this case, we had to adjust the trigger rule of the task joining the branch, done by the join_datasets or join_ERP_branch tasks, to avoid downstream tasks being skipped, because with the default trigger rule, the skips resulting from the branch would be propagated downstream, resulting in all tasks after the branch being skipped as well. In contrast, the none_failed trigger rule only checks if all upstream tasks have been completed without failing. This means that it tolerates both successful and skipped tasks while still waiting for all upstream tasks to complete before continuing, making the trigger rule suitable for joining the two branches. Note that in terms of propagation, this means the rule does not propagate skips. It does, however, still propagate failures, meaning that any failures in the fetch clean tasks will still halt the execution of downstream tasks. Similarly, other trigger rules can be used to handle other types of situations. For example, the trigger rule all_done can be used to define tasks that are executed as soon as their dependencies are finished executing, regardless of the results. This can, for example, be used to execute cleanup code. For example, shutting down your machine or cleaning up resources that you would like to run regardless of what happens. Another category of trigger rules includes eager rules, such as 1_failed or 1_success, which don't wait for all upstream tasks to complete before triggering, but require only one upstream task to satisfy their condition. As such, these rules can be used to signal early failure of tasks, or to respond as soon as one task out of a group of tasks has been completed successfully. Although we won't go any deeper into trigger rules here, we hope this gives you an idea of the role of trigger rules in Airflow and how they can be used to introduce more complex behavior into your DAG. For a complete overview of the trigger rules and some potential use cases, see Table 5.1. Section 5.5, Sharing Data Between Tasks. Airflow also allows you to share small pieces of data between tasks using XCOMs. The idea behind XCOMs is that they essentially allow you to exchange messages between tasks, enabling some level of shared state. Footnote 1. XCOM is an abbreviation of cross-communication. Section 5.5.1. Sharing data using XCOMs. To see how this works, let's look back at our umbrella use case, Figure 5.3. Imagine that when training our model in the train_model task, the trained model is registered in a model registry using a randomly generated identifier. To deploy the trained model, we somehow need to pass this identifier to the deploy_model task so that it knows which version of the model it should deploy. One way to solve this problem is to use XCOMs to share the model identifier between the train_model and deploy_model tasks. In this case, the train_model task is responsible for pushing the XCOM value, which essentially publishes the value and makes it available for other tasks. We can publish XCOM values explicitly within our task using the XCOM_push method, which is available on the task instance in the Airflow context. This call to XCOM_push effectively tells Airflow to register our model_ID value as an XCOM value for the corresponding task, train_model, and the corresponding DAG and execution date. After running this task, you can view these published XCOM values in the web interface in the Admin XCOMs section, Figure 5.16.